We have another example problem here. I pulled this one from our book as well. What are the strength and direction of the magnetic field at the center of the loop in the figure? So down here we have a wire. It comes first straight, then it loops, and then continues on straight. With the way the current is drawn over here on the right, we can say the current is coming to the right over here. As this wire loops, the current is still flowing, 5 amps, and then the wire bends away and continues on. So there's going to be a magnetic field here in the center of the loop. We need to determine both how strong that field is and what direction overall it points in. We do need to consider, so the total magnetic field at the center of this loop okay, sorry, got the whole delay in my computer. The total magnetic field is going to be due to the wire itself. This is essentially a long straight wire that happens to have a loop in it. So we need to add the magnetic field that just having that long straight wire will produce, plus the field that the loop itself will produce. Now, since we're looking at the exact center of the loop, the B of a coil, the one listed as B of the coil on our test notes, is the one that will work for us in the center. We can also use B of the loop and just make Z equals 0, because then we get B of a coil just without the N. So for the wire, I'm going to just solve this on individually for the wire and the loop. On the test notes, we have B of a wire is mu naught over 2 pi d. Now d means the distance from the wire to the location we want to find the magnetic field. So mu naught is our constant, which again, I remember the exact value, so that's the one I'm plugging in. I, the picture shows us, is 5 amps. D, the distance from the straight portion down to the middle. Well, in the picture, they tell us the diameter, or they show us the diameter of this loop is 2 centimeters. The wire itself is a radius, essentially, a distance of 1 centimeter. So D is 1 centimeter away from the wire. So 0.01. The 2 pi's will simplify, so I end up with just 2 times 10 to the 7 on the top. I'm getting 1 times 10 to the negative 4. Teslas. Now we do need to know the direction as well, because when we add these vectors up, we have to account for their directions in the process. So if I think just long straight wire, this is the portion we're calculating for right now, the current is pointing to the right. We want to put our thumb of our right hand, so our right thumb, just hold it out in front of you and point it to the right, to your right. When you do that, you should see your fingertips pointing at you above your thumb, which means if you curled your wrist around to get your fingertips below your thumb, they would point away from you. So the magnetic field that this wire is creating is going to be circles around this wire, coming out on top, coming down, going in on the bottom. Since the center of the loop in our picture is below this wire, this magnetic field at that exact location is going to point into the screen. Okay, so now we need to account for B of the loop. Now, B of a loop or B of a coil is the one I'm writing down, because B of a coil is for just a few number of loops. That's what the N means. And specifically with Z equals 0. So if we only have one single loop and we plug in Z equals 0 into the B of a loop equation, we get mu naught I over 2R. And that's what the equation simplifies to. So the magnitude we can find, we know mu naught, oops. The current is the same current flowing through all of it. R is the radius of the loop itself, which is going to be 1 centimeter. So B of the loop I'm getting 3.142 times 10 to the negative 4 Teslas. Now this number's bigger, just over 3 times bigger than the wire, which hopefully makes sense. The loop, every portion of the loop is the same distance from that point that we're looking at, as opposed to the wire itself. Different parts of the wire are different distances away. Now we do need to use the right-hand rule to figure the direction of this magnetic field as well. So we can either put our thumb in the direction of the current at one point on the loop and use our fingers. So for example, if I look at just where I drew this arrow in my picture, trying to highlight it, there we go. So if I put my thumb of my right hand in the direction of this arrow, on the side of the loop where my dot is, my fingers are pointing in to the screen away from me. They would point out on the other side. That means this magnetic field around the loop is coming up out of the screen towards us, outside the loop, and going in towards the screen in the center. And the point we care about, that we're trying to find the value out, is in the center. So B of the loop will be this 3.142 times 10 to the negative 4 Teslas. And it points into the screen at that location. So B, the overall magnetic field in the center of that loop, I'm just adding these two together. They're both pointing into the screen. They're both in the same direction. So I'll simply add them. And my overall direction will be into the screen. So we have 2 sig figs based off of the numbers given in the problem. So I'm going to round that. 4.1 times 10 to the negative 4 Teslas. And then into the screen. is the direction.